Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Bart de Pontieu. He's going to talk to us about one of NASA Ames and Lockheed Martin's latest missions called IRIS. Bart got a Master's in Physics from the University of Ghent in Belgium, and then did a PhD at Ghent and the Max Planck Institute in Garching, Germany, before he came across to the US on a postdoc and worked at Stanford, and then was immediately employed by Lockheed Martin, where he's been for the last 12 years. Bart's interested in the connection between the sun's surface and its atmosphere. He's a member of the NASA TRACE mission and the NASA JAXA Solar Optical Telescope mission, and he's a co-I on the AIA instrument on the Solar Dynamics Observatory. And today he's going to talk to us about his role in the latest mission called Interface Region Imaging Spectrograph. So if you'll join me in welcoming Bart.
Thank you, Adrian, for the introduction, and thank you for having me today. I'm actually going to talk about IRIS, the Interface Region Imaging Spectrograph, only towards the end of my talk for about maybe 5 minutes or so. The main reason for that is IRIS is being built. In fact, we have the critical design review next week, and it's due to be launched in December 2012, so we have no data of it yet. What I really want to do is, since I was asked to talk about IRIS and why we have IRIS, is to talk about the reason for putting the satellite up there. It's a NASA small explorer mission, and give you a little bit of an overview of what we've learned about the solar atmosphere in the last few years, especially about the region between the surface of the sun, called the photosphere, and the corona of the sun. And you can see a movie of the corona here. And this movie was taken with the Solar Dynamics Observatory, which was launched earlier this year, also a NASA mission. So I'll give a little bit of an overview of what we've learned about the surface and about the corona, and then essentially give you some very recent results that point to the interface between those two regions as being an important one for understanding the full atmosphere of the sun. And this is the work that I'll be presenting towards the end is work I've done with the colleagues mentioned at the bottom here. So let's start with just the basics. We know that the sun is a very dynamic star. This is these are images rather of the sun taken in extreme ultraviolet light with the SOHO satellite, a European-American satellite that's been up there for about 15 years. And what it shows is the activity, the brightness of the atmosphere over the last, well, not the last, but over about 11 years. And you can see there's a cycle here, and most of you probably know that this cycle has to do with the sun's magnetic field. And in general, the fact that you have these solar maximum periods where there's a lot of solar magnetic activity can also impact the Earth. That's why during periods of high solar activity we get northern lights, we get what we call space weather. One of the main reasons why we study the sun is to understand how it impacts the Earth, and space weather is an important aspect of that. Solar activity itself is driven by internal flows inside of the sun, by convection, by turbulence, and magnetic fields, and all of these are coupled on a variety of spatial scales, from very small that we can barely resolve with our telescopes from the Earth to very large on the global scale. The flows inside of the sun essentially spread this magnetic fields, and when they pop up to the surface, they get generated inside of the sun, they pop up to the surface, and they drive all kinds of activity. And we'll talk a little bit about the popping up and about the activity that we see higher up. So let's start a little bit with just the basics of the sun. This is a cut of the inside of the sun, and we have the core where nuclear fusion happens, where atoms get smashed into each other, and that releases a lot of energy. That energy is radiated through the radiation zone outward. by about this distance from the core, the sun's interior becomes too opaque to really allow radiation to carry the energy. And when that happens, convection sets in. And convection is really the same process that you have when you're boiling water on the stove. The energy actually gets transported physically by the mass, by the gas itself. It's popping up in the pot of boiling water. It's the water that gets heated at the stove, pops up to the surface, radiates its energy, cools down, and falls back down. And so there's a cycle there. And that happens in the last part of the interior of the sun here. This is what we call the convection zone. Somewhere between the radiation zone and the convection zone is where we think most of the magnetic field of the sun is generated. The sun's magnetic field is very different from the Earth's magnetic field. Well, it's similar in many aspects, but the sun's magnetic field is much more dynamic and has a lot more complexity to it when it pops up to the surface. When you get to the surface, that's where most of the light that we observe comes from, especially the visible light, and it's called the photosphere. And then just above it is the corona. And the really interesting thing that has been puzzling solar physicists for the last 60 years, ever since they realized that the corona is extremely hot, is that as you go from the core to the surface, the core is about 15 million Kelvin degrees. As you go out, the temperature just essentially keeps dropping, and it's what you would expect intuitively if you have a candle. You put your hands really close, they're ready to burn, and as you move your hands away, it just gets cooler and cooler. Up to the photosphere, that's the case, and then it's cooled down to about 5,000 degrees or so. And you can see that in this plot here, which shows the height above the photosphere here. And you can see here, this red line here, this is where the photosphere is about 5,000 degrees. The really strange thing is that as you go up a few thousand kilometers, which sounds like a lot, but is actually just a tiny little blip here, it's about the size of a letter here, the temperature jumps back up to about 1,000,000 degrees. And that's what happens in the corona. And so the corona is millions of degrees hot, and there's a lot of theories why this happens, and it has to do with the sun's magnetic field. But the details of what's happening there are what a lot of the solar physicists that I work with are studying. It's one of the main problems of solar physics. Another main problem is how the magnetic field gets generated. And then another problem is how the solar wind gets accelerated, and I'll get to that a little bit later. One other interesting thing to consider, though, is that as you go from the surface to the outer atmosphere, which is here, the density actually drops by many, many orders of magnitude and becomes very low density. So the corona is very hot, but it's also very low density. The photosphere is much, much more dense, is cooler, but actually has a lot more energy. And the region in between these two, photosphere and corona, is called the chromosphere. There's also a transition region where the temperature really jumps up like that. And the chromosphere and transition region together is what we call the interface region between the surface and the atmosphere. That's the region that IRIS will study. I'm going to talk mostly about results in the photosphere and the corona that have been pointing to big fat fingers and arrows to this region for why we're having trouble understanding what's happening in the atmosphere. So what does the photosphere look like? That was a wiggly line plot. Now we can zoom in from full disk all the way to the smallest details that we've been able to resolve with actually in this case a ground-based telescope in the Canary Islands. And what you can see is that there's a lot of, I'll try to use my mouse so people don't feel excluded on the right side of the auditorium. What you can see here is essentially these convection cells, these bubbles of plasma that bring the energy from the interior of the sun to the surface, radiate most of the energy when they're at the surface, and that's why we can see it with our telescopes. And that's these bright cells. And then the dark rings around them are what we call the intergranular lanes, where the plasma actually is cooled down and falls back down. These things are all over the sun. So they essentially, the whole surface of the sun is boiling. These little bright points that you see here seem very insignificant, but actually are very significant for the topic at hand, which is the heating of the solar atmosphere. They're sites of magnetic fields, strong magnetic fields. You can see a very strong region here, which is what we call a pore, a dark region. And then you've got all these little bright points that are little flux tubes, we call them, magnetic flux tubes. And when you take a look at a movie of that, and this is going to be a movie made by the Japanese Hinode satellite. It's been launched in October 2006 and has been observing the sun since then. It's in a sun-synchronous orbit around the Earth, so it can see the sun most of the time. It has significant contributions from both NASA and Europe. And it traces essentially the magnetic fields in the photosphere very well and the corona, and has a little bit of a gap in the middle. It has made the most sensitive measurements of the sun's magnetic field ever. If you take a zoom in of the instruments, I'm going to be focusing on results from the optical telescope assembly, and in particular the focal plane package instruments which Lockheed Martin in Palo Alto built, the lab that I work at. What that does is it takes images and spectra of the surface and the region just above the surface of the sun. And if you look at a movie of the solar surface, the photosphere, you can see that it's highly dynamic. There's a little clock running here, and on timescales of about 10 minutes, these convection cells that I pointed out in the still before are completely gone. And that's essentially what you're seeing when you're boiling a pot of water too. There's a lot of dynamic stuff going on. There's a lot of noise when you boil water. And similarly on the sun, there's a lot of noise as well. And there's a lot of energy in that acoustic noise. You can also see, when you zoom in a little bit more, that these little bright points here are continuously shaken about and are essentially at the whim of this boiling plasma. Yeah.
The size scale of these?
Oh, yeah, that's a very good question. This is about the size of the Earth here, this square, except that it's a square. And not, so each of these cells is about 1,000 kilometers or so. The little bright points are usually about the size of a few hundred kilometers. So what you can see is that these little bright points, these magnetic fields, they anchor the magnetic field of the sun, just get shaken around. And this is where the sun's magnetic field is very different from the Earth's magnetic field. The Earth's magnetic field, just essentially comes out of the poles of the Earth, comes out of the poles of the Earth and is quite stable over timescales of, 5 minutes. This is, as you can see here, just an hour's worth of data. That's not the case in the sun's atmosphere. And what happens when you do that is that you're transporting a lot of that acoustic power and that convective power into the magnetic field. And you're actually, magnetic field lines, when they're shaken like that, they actually behave a little bit like rubber bands, as in they can be twisted, they can be moved around. And when you build up enough twist in these field lines, in these magnetic field structures, the rubber bands can snap. And in that case, you get what we call magnetic field reconnection. And that releases a lot of the energy that was built up by shaking the foot points higher up in the atmosphere. That's kind of, in a nutshell, what people think is driving the heating of the corona. But there's a lot of discussions about how that happens in detail. And we'll get to that a little bit later. But fundamentally, what you're seeing in the background heats the corona, drives the solar wind, and causes flares and coronal mass ejections. So then comes the Solar Dynamics Observatory, which was launched in February. It's NASA's Living with the Star flagship mission, first one. And it observes the sun continuously. The instrument that we built is up here. That's the atmospheric imaging assembly. And you can see it here in the lab. And it consists of 4 relatively small telescopes that observe in the extreme ultraviolet. So they're very sensitive to emission from highly ionized plasma, which we know occurs in the corona. And so it's a very good way of imaging what happens in the corona. It's in a geosynchronous orbit, sorry. And it's got 4 telescopes, which each have sensitive to essentially specific wavelengths. This is in angstroms here, so we're looking at the extreme ultraviolet. And the little curves we're not going to go into here, but they essentially show the sensitivity to different temperatures. This is the logarithm of the temperature here, and you see this one is sensitive about 1 million, whereas this one is more between 1 and 10 million. And so we also take images of the surface of the sun with AIA in the visual light. And so if we kind of take a step through from the photosphere up into the corona, we can also make measurements of the magnetic field, and that's with the helioseismic and magnetic imager on board the same spacecraft, and that was built in a collaboration between Stanford and Lockheed. And that takes what we call magnetograms, And what these are, they essentially show where the magnetic field of the sun is strong and which polarity it has. White is essentially one polarity and black is the other polarity. And so if you go back to the Earth's magnetic field, this would be like the North Pole and this would be the South Pole, except that of the magnet that's connecting the two. But except that you can see that there's black and white all over the sun. So it's a much more complex picture than what you have on the Earth. You can make calculations of what the magnetic fields do in the atmosphere based on what you measure at the surface, and you can then go and compare that to the corona. So we're still just looking at the surface, but then if you look at the corona looks like this. Very, very different, highly structured, and as it turns out, it's highly structured because it's structured by the magnetic field lines. So if I go back to this and compare to that, you can see quite a bit of similarity. Some of these linear structures that you see in here, we call those coronal loops. Those are following the magnetic field. And I should remind you that when we're looking here, we're looking at gas that's about 5,000 degrees, and this is about 1,000,000 degrees, 800,000 degrees. So it's a lot higher, and it's only the distance between these two regions is very, very small. So as you go and walk up in temperature, there's one of the things that we can do now. You can see that the atmosphere changes considerably to the point that some regions now have almost no emission at 5 to 9 million degrees. So the really hot parts of the solar corona are confined to the region where the magnetic field was strong. If we go back here, if you looked at the surface of the sun, it looks kind of bland and boring, but the magnetic field really structures a lot of what we see in the atmosphere. One last point that I forgot to make was that we're getting an enormous amount of data from this instrument. It's about 1.5 terabytes per day. It's about 300 movies on a DVD per day, because we're taking images in all of these wavelengths every 12 seconds at very high resolution. And what that allows us to do is to take and get a full view of what the whole atmosphere of the sun looks like at any one time and how it reacts, how it connects globally, which is something we've never been able to do before. So we can also make things like multicolored maps, which now essentially show where things are hot is red, where things are cooler, but cooler is still about 800,000 degrees, they're bluish, and where they're white, they have essentially all of those temperatures. So it's a very complex kind of atmosphere that we're encountering in the last few months, and we're still very much at work trying to figure out what it's all telling us. If we zoom in a little bit and walk around, you can see the enormous complexity and actually also the beauty of the sun in the extreme ultraviolet. This region here is one of the poles of the sun, and as you can see, it's cooler. It's only bluish here. And what's different about this region is that the magnetic field, whereas before a lot of the structures that we saw were loop-like, like they returned back to the surface, the magnetic field here doesn't return back to the surface. It gets dragged into what we call the solar wind. And I'll get to the solar wind in a minute. One of the things that it allows us to do is, again, is to image every 12 seconds the whole sun. And what you're seeing here is actually an image or a movie in the interface region. It's about 100,000 degrees. It's really the gas that's between the surface and in temperature at least, between the surface and the outer atmosphere. And what you're seeing here is, if I play this movie again, is if you look at this region here, these dark features are essentially being thrown out. It's a filament eruption. It's this cool gas that's being propelled outward into the solar wind, into space, because too much stress has been built up into the magnetic field, and at some point the field snaps and throws us out. This is one of the major study areas too, because these kinds of eruptions have big impacts on the Earth, potentially. This is a multicolored movie of the same region, and you'll see the liftoff here. It's a little bit harder to see probably in the extreme ultraviolet, but something takes off here. And the interesting thing is that almost at the same time, a flare goes off, and so there's all kinds of new loops. You can also see this kind of frontier marching in that general direction. I'm not going to go into a lot of detail here. I just really wanted to show you some pretty movies. There's another eruption going on here, but one of the major results that we found so far, other than the one I'll talk about later, is that the global connectivity is enormously important to understand why certain things happen when and where. We've now found many cases of eruptions happening here, and then those eruptions interacting with some magnetic fields here and triggering something here, and then something on the backside of the sun takes off. And so these, what we call sympathetic events, had been reported in the past, but nobody really believed them because we didn't really have the full kind of coverage that we have now. And now it's, you can really trace those things. So what about the solar wind? The solar wind is the stream of charged particles that, is continuously emitted by the sun. And you can kind of see the background of it here. There's big disturbances on top of it, but you can kind of see these rays that just go out of the sun. We all kind of live in that solar wind. The Earth just plows through the solar wind continuously. Mars does too, all the planets do. You can see a comet passing by here in this case. This is a movie made with LASCO instrument on board of SOHO. And you can see the stars actually in the background. One of the major unknowns here is how this solar wind is formed, how the gas is accelerated to velocities of 1,000 kilometers per second. One of the ways to do this kind of thing is using magnetic waves. And the idea has always been that this convective motions shake and jiggle the magnetic field of the sun, and then creates what we call Alfvén waves. And Alfvén waves are kind of like guitar string waves. When you pluck a guitar string, it goes like this, and it propagates in a certain direction. The same thing happens with Alfvén waves on magnetic field lines. So when you shake the field, it'll, this shaking will propagate along the magnetic field lines. What's nice about Alfvén waves is they don't really dissipate very easily. And the reason why that's nice is because sound waves, for example, that are created in abundance at the surface of the sun very easily get absorbed and dissipated. They form into shock waves, and they don't really make it into the corona very easily. Whereas Alfvén waves can go through that intermediate zone, the interface region, and make it out all the way out into the solar wind and then deposit their energy there. But I'll get to Alfvén waves a little bit later too. Yes?
The dark band coming down at 35 degrees?
That's an instrumental artifact. That's what's holding up the cone that's keeping the real sun, or the surface, the visible surface of the sun is a little white line, and then there's an occulter that blocks that light. This light is extremely faint. It's orders of magnitude, many orders of magnitude fainter than the surface. So the corona is very finely structured. This is a movie from Trace, actually, that shows a filament eruption. But you can also see there's a lot of dark features that kind of pop their head up and stick out into the corona. The corona itself are all these coronal loops, these loop-like features that are continuously changing. So what I'm going to talk about a little bit later in the talk is how sunspots form. And we're going to really start with how the field makes it up into the surface and how well we understand that. Then I'll talk a little bit about how we've discovered this enormous amount of weak fields. Sunspots are pretty strong fields. It's where the field is really strong, and it's so strong that it suppresses the convection and makes the surface of the sun look dark. The weaker fields are actually probably more energetically significant, and those we've discovered with Hinode. Then I'll talk a little bit about how the magnetic field potentially impacts the chromosphere, this region in between the two layers, how the solar wind is accelerated, and how the corona is heated. And then these last three here, I'll really talk about how all of these topics are pointing towards the chromosphere as being an important region. So what does the chromosphere look like? Well, Hinode has shown us some really unprecedented kind of activity and movies of the chromosphere. Now we're looking at gas that's about 20,000 degrees, so intermediate between the surface and the corona. And as you can see, it's extremely dynamic. There's a lot of finger-like features that just stick up and fall back down. There's all this kind of wacky stuff that we barely understand. And it's really sandwiched between the photosphere and corona, but it's actually also really intermingled with coronal plasma. It's very hard, in the past, in solar physics, we've really studied the sun's atmosphere in terms of layers, because we were thinking in terms of one-dimensional kind of wiggly line plots like I showed in the beginning, but in reality there's all these fingers there's all this intermixing between these two regions. And the interesting thing about the chromosphere is that it actually requires 10 to 100 times more energy than that whole wide corona that you see out there. Even though it's a tiny little region, it's just the first few thousand kilometers. And so in some sense, if you heat the chromosphere and there's a little bit left, you can heat the whole corona. So it's a topic that has been understudied because it's been very hard, and I'll get to that a little bit later. So when we talk about the formation of sunspots, this is a movie of sunspots from Hinode, and you can see a lot of dynamics in here. There's the really dark region called the umbra. There's the penumbra at the edges here, and here's the diameter of the Earth. And you can see a lot of filamentary structures, and we know that the magnetic field here is very strong, but why all these dynamics are going on and how these things form has been a little bit of a mystery. This is a cartoon of how we think is going on. We got magnetic field lines, these white things sticking through the surface. We're coming from the inside of the sun and we're popping through the surface now, and then these magnetic field lines, these loops, connect. So that's the animation. The observation.
How does that cool the sunspot then?
When the field is really strong, it'll suppress the convection because the gas can't do its little motions anymore. And when that happens, you're losing a source of energy. You're not fully losing it, but you're losing quite a bit of it, and that leads to so the funny thing about sunspots is that it cools down at the surface, but the energy that, the whole active region, the energy that you're still putting into the field actually makes it brighter in the atmosphere. So there's a little bit of a different effect there. Hinode has essentially allowed us to really see how these things pop up on the surface. This is a magnetogram again, and if I go back, if you look at this region here, you start seeing this enormously complex region of black and white little things, and then there's this sunspot forming here and a sunspot forming there. There's some pre-existing ones here. And you can now do amazing things thanks to Moore's law, amazing things with the computer. And one of my colleagues at Lockheed has done really amazing simulations, Mark Chung, that essentially simulate that whole outer layer of the sun's interior convection zone. And what he's done is calculated over, using thousands of CPUs at the same time for millions of hours, what would happen if you introduce a magnetic field at the bottom and how that pops up and how it gets, pops up to the surface. And if I start that movie again, purple is essentially what we would see with a visible, with our naked eye, which we had a good telescope. And then here pops up the magnetic field. Red is one polarity, and blue is the other, so that's where the field is, popping out vertically through the surface. And then green is the stuff in the middle. And as you wait, it becomes very psychedelic. You start seeing two big fat sunspots here. And they actually show a lot of rotation, which is what we also observe with our other telescopes on the sun. And that usually leads to things like flares and CMEs. So these kinds of simulations have been just hot off the press in the last year or so, been very amazing and teaching us a lot about what kind of dynamics we see there and why things are cooler. And if we then go to the quiet sun, as we used to call it, and we still call it that even though it's really not quiet, there's no sunspots here on this magnetogram. All these little points here are things that are relatively weak, but there's so many of them. And with SOHO we discovered that there's a lot of them on scales what we call supergranules, very large scales, 30,000 kilometers, 20,000 kilometers. So between these little arrows is like one supergranule. If we zoom in on that and make a movie of it, we start realizing these little circles that new magnetic field pops up or gets canceled. And when I say canceled, I mean black and white hit each other, and that means it either retracts or it reconnects and throws up something. And that happens all the time on the sun. In fact, all of this weak field is recycled on timescales of about 10 hours. So there's a lot of magnetic field that's just continuously being popped up and then recycled through the convection. The convection just kind of pulls all this stuff up and down. What we've discovered with Hinode is that when you look on even smaller scales, this is now one of our big cells that we looked at before. Now we're looking at even smaller. We're seeing the same kind of stuff, all these little white and black dots. It looks maybe a little bit arcane to you and noisy, but it's actually very fundamental. There's so much weak flux that we never realized was there, that if you sum it all up, it has so much more energy than any of the sunspots over a whole cycle. And so we think that's a lot of this stuff is what's driving the atmospheric heating. And making that connection between these things and what happens in the atmosphere is one of the goals of IRIS. This stuff is happening on such small scales. When I say small, it's about 1,000 kilometers. It gets recycled on about 10 minutes or so time scales. And we know that that leads to a lot of activity in the chromosphere. We've made some tentative kind of connections between what happens with the fields and the chromosphere. The chromosphere is shown here. And a lot of these little brightenings and little fingers that shoot up are related, especially these kinds of events, to little magnetic field popping up, interacting with pre-existing magnetic field, leading to reconnection of the field, and then throwing stuff up. And you can see a nice movie of that in here. It'll take a while to start, but if you look in this region here and then follow this explosion here, you can see there's some wiggling going on, and that's one of these Alfvén waves. This is the magnetic field being shaken. Matter being accelerated over to very high velocities in a very short time. We're talking a few, the Earth itself is about this size here. These kind of events happen all the time on the sun. What I've been studying in the last few years are these things. Not the big fancy ones that occur every now and then, but the ones that are really small and that are continuously there. And these are called spicules. And spicules have been around for a very long time, but we used to observe them with an instrument that was able to do this. What I essentially did is I took Hinode data and ground-based data and reduced it to what we used to have. Essentially, a spatial resolution that was pretty poor, and we could only take an image every 30 seconds. And it was very hard to figure out what was going on, especially when you realize what's really going on at the same time is the stuff on the right here. And there's almost no connection between, there is obviously a connection, but it's very hard to, understand how things evolve and how they form when you know that the time scales are much shorter and the spatial scales are much finer. And what we've quickly realized a few years ago when we had the new data was that there were two types of events going on which hadn't been recognized. There's these kind of slow pokes that, they're not that slow, but they're 20 to 40 kilometers per second. They kind of go up and down. They have pretty long lifetimes, a few minutes. A lot of these movies are accelerated, by the way. This is essentially every image here is 8 seconds. We take an image every 8 seconds, and you can see that there's a lot of changes on very short time scales. But the second type is hard to see here, but there's a lot of twinkling in the images. And if you go at the poles, you see this new type. And one of the things that we realize is that this stuff is about 20,000 degrees hot, and we see it just go up. It doesn't come back down. None of this gas comes back down. Clearly, we know that there's a lot of mass in these things. We know that it has to come back down somehow, but it's not coming back down at the same temperatures that it's being thrown up. This is 20,000 degrees, and what we've now shown, and I'll show in a minute, is that when this gets thrown up, it's actually also being heated, and it comes back down much hotter than it was being thrown up, and that's why we've missed it in the past. People have speculated about this, but haven't been able to show it, and with the new instrumentation, we have been able to show it. But actually, one of the things that struck us first was that there's a lot of wiggling here. A lot of these things wave around. There's like waving grass, essentially. And we know that these linear structures outline the magnetic field, and we know that when you see this, that's a sign of an Alfvén wave, or it can be a sign of an Alfvén wave. And so we studied that in detail. We looked on the disk. This is in the light of hydrogen, H-alpha line. Pretty weird-looking stuff, but what we realize is when you look at a lot of these linear features that are being thrown up and come back down, is that they're also shaking. Essentially, the whole chromosphere is shaking continuously. And when you look at it in detail, you can actually see it here. There's a little feature forming, and it moves to the side. But the feature doesn't live very long, and so you don't see the full wiggle. You only see a little piece of it, and then by the time that it's supposed to come wiggle back, it's being heated out of the passband that we're using here. We're only sensitive to light that's from singly ionized calcium, and it's only 10,000 degrees. And so if you're throwing something up and it's on a field line that's shaking and it's being heated at the same time, you won't be able to see the full evolution of that. One of the revolutionary things about Hinode is, again, the spatial and the temporal resolution. We never had that before. And having a space-based instrument really helped us there, because ground-based data often has the Earth's atmosphere makes our images look blurry, just like on a hot day when you're looking at a highway, you can see the air just kind of shimmering. We have that all the time when we're looking at very fine details like that, and we use adaptive optics to try and compensate for it. But space-based instruments really are better for that. Yes?
These pictures are being shown at some narrow wavelength.
Yes.
It shows the ionization. If the temperature of the gas is changing, it may pass out of
Yes.
the wavelength. So you really need multiple
Yeah, you're making a very good sales pitch for IRIS, because IRIS will do that, so thank you. That is exactly the point I was trying to make, is that it's very hard to figure out what's going on if you just have one. And that's why we built SDO, which has all of these wavelengths. But SDO is trying to look at the global connectivity. We're really trying to be the microscope to SDO in some sense. So when we looked at at numerical simulations from our colleagues in Norway, my collaborators in Norway, what this shows here is the little red lines are essentially magnetic field lines, and you can see them shaking about. We're showing about an hour's worth of evolution on the sun here in a box. So we've taken a box, a numerical box, and we have a little bit of a convection zone, a photosphere, a chromosphere, and a corona. And making all of that work in one is very hard, because as I showed earlier, the density changes enormously from the bottom of this box all the way to the corona. There's, 5, 6, 7 orders of magnitude difference in the density. And that makes it very complex to make this calculation in any kind of reasonable time frame. But thankfully, the computers at NASA Ames have been very useful for us to, do these very intense calculations in a human kind of lifespan kind of way. It takes about a month or so, or a few months to calculate these kinds of things. And what they're teaching us in the red field lines, the red lines are the magnetic field, the reddish hue and the green hue are essentially the chromosphere, is that these shaking waves are very similar in the box to what we observe on the sun. And using a comparison between these two, we're able to essentially estimate how much energy is in the waves. And what we found was that the energy was, this is a plot from a group of people that have done theoretical calculations of what they need to accelerate the solar wind using these Alfvén waves. What they found was that these lines here, this is the distance from the surface all the way out to the Earth. Well, not quite the Earth, but 100 solar radii. And this is the amplitude of the waves that we need, that they need for their model. And what we did was we added a point here that essentially says, yes, you will have enough energy to do this. Which is very exciting, but at the same time, the waves that we see have much lower frequency. They're really slow. They take a few minutes to kind of wiggle around. A lot of the theoretical models that assume that there's dissipation going on in here to accelerate the solar wind assume much higher frequencies, and so that has led to some reconsidering of these models. We're providing constraints on what they can do. Another thing that we've been focusing on is with SDO is that when you look at a movie like this is the original data, it looks like you have nice loops and they're just sitting there and everything's hunky-dory. But if you take a running time difference, so essentially what we did is we took this movie and each image we subtracted the previous image. Then we're focusing on the changes. Then what we realized is that, and people have known this for a while, but not that it's quite that ubiquitous, that there's a lot of dynamic changes in here, and there's actually kind of propagating disturbances that just continuously propagate through from the foot points into these coronal loops. And what we've been able to do is link those to our spicules, to our jets. And this is kind of the complicated scheme. We have this is the chromosphere. This is actually the magnetic field. Bright here is magnetic field. In sites of very intense magnetic field, we get these little spicules. How they form, we do not know. But they get heated somehow. And how that happens, we don't know. But we find evidence for using spectra and using images to essentially show that these things get heated and lead to propagating disturbances in the loops like I showed in the previous movie. I'm going to kind of skip this. One of the things that we've done very recently is we've looked at how that process actually happens. And the previous slide was a little bit of more of a speculation of ours 2 years ago based on various pieces of the puzzle. We've now been able with SDO to actually pin this down, and we've submitted this to science, and hopefully it'll get accepted, but we'll see. This is an image of the photosphere of the surface, and we're now going to take a trip from the photosphere into the chromosphere using the H-alpha line. We're going to scan through this line, and as you scan through the line, you essentially become sensitive to different layers of the atmosphere. So we're starting at the surface, and we're now moving into the chromosphere. And as you can see, and then back down. And we're doing this a few times. As you can see, the structure of the atmosphere changes completely from dominated by convection cells here to things that really dominate by the magnetic field. These kinds of instruments are on the Swedish Solar Telescope in the Canary Islands. And with this kind of data, we've been able to, when you look at a movie of this, you're seeing here the top of the chromosphere. And here in the background, you're seeing the surface of the sun. You're seeing the site of all these magnetic fields, these bright points. But you're also seeing, and it's a little bit hard to see, these black things that are shooting out. And these black things are our spicules on the disk. We've never been able to, for the last 40, 50 years, as long as spicules have been studied, we've never figured out what they actually look like on the disk. We now know what they look like on the disk. You have to go out very far in the blue wing of H alpha, and you're essentially using the Doppler effect, the fact that the frequencies of the light change when plasma is moving towards you. And so when you go out to the blue wing of H alpha, you're starting to see plasma that's being thrown up at about 50 to 100 kilometers per second or so. And so we discovered these last year or 2 years ago. And so using these, we can then go and see what AIA, what the Solar Dynamics Observatory sees at the same time. And that's what this movie is. And this looks really noisy, and in some sense we're really pushing the instrumentation here. But IRIS will be able to do this a lot better and more convincingly. But what we're essentially seeing here is this dark feature here is cool plasma being thrown up. And what we're seeing here is the same time and co-line. This is from Hinode, from the Japanese satellites. These all are from the Solar Dynamics Observatory, launched earlier this year. And what we're seeing here is little brightenings that are associated with this dark, cool thing. And the brightenings are all in hot lines. This is about 100,000 degrees. This is about 1 million degrees. And this is about 1.5 to 2 million degrees. And while it's hard to see the little blob, and you might say, well, why is he studying these blobs? The reason why we're studying these blobs is we find them everywhere. And if you do a little bit of image processing, again, this running time difference, you can really nicely see how every time you throw one of these chromospheric jets up, there's also plasma getting heated to a few million degrees. And what that does is it puts the whole focus of coronal heating, which has always been in the whole corona, to really the foot points. Maybe all that heating is actually happening low down in the interface region. This is not something that people have been considering very seriously, except for maybe in the 70s. One of the reasons they haven't is because it's really hard to study this interface region for a variety of reasons. One of the reasons why we're excited about this is because these little red things are all the jets that we find, and we find them everywhere on the sun. So everywhere we look, we find chromospheric jets that are associated with coronal heating. And now we have to convince our colleagues that that's really the case, but that's another story. What we don't know is how these jets form, and we don't know if they really provide enough plasma to heat the corona. And those two questions will be one of the two questions, two of the questions, main questions that IRIS will be able to address. Because IRIS will be able to observe the whole region in between the surface. We'll have much better instrumentation than even though these instruments are wonderful, they're relatively low resolution. The features are very fine, and AIA doesn't really resolve them. And Hinode doesn't have the thermal coverage. And so we'll be able to do that with the Interface Region Imaging Spectrograph. And what that is, we're building this at Lockheed Martin. My boss, Untitled, is the principal investigator, and we're working with NASA Ames, Montana State University, Smithsonian in Boston, in Cambridge, Massachusetts, Stanford University, and University of Oslo. We're seeing here a telescope, and this telescope is a UV telescope, so it observes in the ultraviolet. And it'll be able to track both the chromosphere, transition region, and corona all at the same time with a very high sensitivity. And I can show you that here. The reason why IRIS will be very, very nice for a lot of our studies is because it's really got much better spatial temporal resolution than any instrument that we've had before. And this is illustrated here. What I'm showing is a movie that Hinode took of an event where there's some heating here. And what I'm showing is what SOHO observed. When I'm showing you the SOHO slit that was moving, it's an imaging spectrograph, so it has a slit that was moving across this event. And this is the output that SOHO would have produced if it had been pointed at that region. This is the output that Hinode would have produced. And as you can see, it's very hard to keep track of what's happening here based on just these two rasters, but that's all we have right now. We can't really figure out what's going on in these kinds of events, and that's what we need to figure out if we want to figure out how the sun's outer atmosphere is heated. IRIS will be able to give you this. It'll be able to image the environment and provide spectral information in that raster here. And so with that, and combine that with numerical simulations that are like the new pillar of our field, because they really are allowing us to study this region. The reason why this region is so complex is because the radiation in this region is very hard to interpret for reasons I don't have time to go into. And you need computer models to really catch all of the complex physics, the non-local radiative transfer, essentially. And what we can do is we can simulate a box of the sun, and we can look at spectra that we simulate, and we can compare the properties of the spectra, and then in a statistical manner do comparisons what we observe to figure out what kind of physics are dominating in the real sun. And one of the preliminary results of these simulations is that indeed the heating is all pretty much localized low down. What we're seeing here is a cut at the surface, and we're seeing these magnetograms with the magnetic field of the sun being shaken about by the convection. And what we see, that's in black and white, what we see in color here is a lot of heating events. And they're very short-lived, and they're very linear, they'll almost look like loops, but the actual corona is up here. So most of the heating is actually happening low down in the interface region. And you can see that here from the side. These are essentially synthetic observables that we've made from the simulations that we'll be able to directly compare with IRIS. And with that, I'm going to end with a slide of something that we really don't understand, and I have no idea when we'll understand it. It's a little bit hard to see, but there's a lot of prominence material here, which is cool material that's lifted to very great heights that we wouldn't normally expect this kind of plasma at. And as you can see, there's an enormous amount of turbulence and complexity there that is also something that IRIS will be able to study. But this is really my conclusion slide. We understand sunspots a lot better, how they actually form deep down, how the magnetic field is generated, the dynamo of the sun remains puzzling. We've discovered a lot of very weak magnetic fields, and even though they're weak, they have a large potential impact on the atmosphere of the sun. And that impact will need to be studied with IRIS. We've looked at alphane waves, these magnetic waves, and we found that they carry enough energy to drive the solar wind, but how they form and how the dissipation happens is unclear. And we've shown that these jets provide hot plasma to the corona. We don't know how these jets form and whether that's really the dominant source of coronal plasma or if that's just one of them. And IRIS will be able to do a lot in that direction as far as answering a lot of these questions goes. And thank you for your attention. That was it.
But just in that, in this video, it seems like there's some interactions with this region here.
Hold on, there.
That are causing what looks like convection cells there, just above the spicules.
Well, this is a very special region. Typically, the spicules don't have this thing happening at the same time. This is what we call a prominence. And these are the ones that when they erupt, they provide all kinds of fun in the solar wind and cause space weather. In this case, you're right. It looks a lot like convection, and it's a very hot topic in our field. It was discovered with Hinode, because you really need the fine resolution to see this stuff. We could never see this from the ground before. And there's all kinds of weird effects, probably from interactions between neutral plasma, neutral gas and plasma and ionized atoms. There's instabilities going on here. There's interaction with magnetic field. I think there's a cavity coming up here that interacts with these things. It's a big mess, really. We don't understand what's going on in this region. It's a topic of very focused science. Yep.
Thank you. My question is about one of the early slides you showed with the solar atmosphere's structure, and it showed the density getting low, but there, that one.
Yep.
Why is the green line dotted when you go closer to the sun and below it? Is that because they don't have actual reliable measurements of the density?
No, I stole this slide from the web somewhere, and whoever made that is responsible. No, we have very reliable measurements of the density all the way into down to the core. So it's really just an artifact of the curve. I'm not sure what I think they were trying to show what happens from the chromosphere upwards. But the one thing to remember, of course, is this is some average, some spatial and temporal average. In reality, there's enormous differences. When one of these chromospheric fingers sticks out into the corona, that density goes up, by several orders of magnitude right here. One of the problems in our field is that a lot of theorists have been, this is being taped, right? Have been thinking in terms of one-dimensional models and ignoring the complexities of the fact that the sun is actually a three-dimensional object with a lot of structure.
How does the temperature vary within the chromosphere?
We have very poor diagnostics of that.
Okay.
There's actually a very, there's a debate about, we're observing in carbon monoxide lines, we're seeing some very cool evidence of some very cool plasma in the chromosphere in regions that are non-magnetic. But it's very hard to reconcile that certainly with a 1D picture, because it doesn't fit with the 1D picture. The chromosphere is essentially defined, in the 1D model as something where it gets hotter than the temperature minimum, which is right here. But there's some regions where the temperature is only a few thousand degrees, apparently. How they fit physically within the whole atmosphere, and when they occur and why they occur. Some colleagues of mine were working on that right now. From the simulations, you can put some limits on what happens there. So I would say between 2,000 and probably 20,000 degrees, somewhere in there. Most of it between 10 and 15 or so.
Is there a correlation between the magnetic field density and the temperature? That is, can you map three-dimensionally the magnetic field densities and how they relate to actual perceived temperature?
There's a correlation, a very nice correlation over many, many orders of magnitude between the magnetic field magnetic flux, I guess, magnetic field, magnetic flux density, and the X-ray luminosity, and also the EUV and the UV luminosity. And so we can see that wherever, if you stay low down enough, because when you do these spatial correlations, once you get out into the corona, the field lines tend to, no longer be directly above where they're rooted. But if you stay low enough, you'll find a very nice correlation on large scales between those properties, and it's a power law over many scales. So there's clearly a correlation there.
Can the degrees of freedom of the magnetic field as you go higher and higher in the coronosphere allow you to have a higher temperature because you're no longer constraining the vectors by the magnetic field, the velocity vectors of the particles?
The expansion of the field happens lower down than where you actually get the coronal plasma. So that is not, we should probably discuss this offline, because I'm not quite sure I understood your question fully, but the field expands in the chromosphere, whereas the hottest plasma is actually happening above the region where most of the expansion has happened.
Bart, I have another question. Now, in the video you showed with the comet coming across, how was that image actually taken? And also, you mentioned that the solar wind has some relation with the pole, but most of the solar wind stuff seems to come out from the equator of the sun.
Yeah, there's a fast solar wind and a slow solar wind. The fast solar wind comes out of the poles, the slow solar wind comes out of the equator regions where there's the genesis of the slow solar wind is a little bit of a discussion still. I was just mentioning it because you could nicely see the poles there. This image is taken with an occulter, with a coronagraph, essentially. What that means is that they have a normal visible light telescope. I think this is visible light, and they put an occulter somewhere in the middle. They keep the sun's visible surface hidden behind that, and then they have to have very, very good optics to make sure that there's not too much scattering within the instrument, because any kind of scattering from the surface of the sun would wipe out any of the signal that we're seeing here, and then you just image what's left. there's been a lot of discoveries of comets have been made using this data. They've discovered hundreds of very short period comets and ways that you normally can't observe because they're so close to the sun.
Is there a reason we're not seeing we're not seeing much stuff coming out of the polar region there?
Yeah, you can see these kind of plumes that are sticking out kind of more continuously. The active regions are all towards the equator, so they're not at the poles. And the active regions are the ones that are providing a lot of are leading to a lot of the activity in the solar wind. So these, what they call coronal mass ejections, that's what we're seeing here, these burps that the sun periodically lets out. And those will not typically occur towards the poles.
And so does it follow that the spicules aren't found in the polar regions, or?
No, actually they're found everywhere. They have very different properties though. At the pole they're taller than they are in the quiet sun or in the active region. In the active regions they're smallest. The differences between those, of the properties between those regions are also something that we're studying and why that's happening.
The images of convection cells do they look the way they do with brighter areas simply because of the temperature? That is, that the brightness is a direct indication of the temperature?
Yes.
Thank you.
Yes. Well, with one exception, which is that these... No, I guess that's right. Yeah, it really is always, it's the temperature. You're looking here at these little bright points here. The reason why they're bright is because the magnetic field it's kind of like a flux tube, and within that flux tube, the plasma is evacuated. It's actually lower density, and so we're actually looking deeper into the surface of the sun. And so it's kind of, and that's why, and there it's hotter deeper into the surface, deeper into the interior of the sun. And since it's hotter in the interior, it's brighter, and that's why these little things are bright. We used to think 5, 6, 7 years ago, well, some people thought that this was because there was actually heating happening there. But at that height, there probably isn't much. It's really just a hole in the surface effect in some sense.
Okay, well, Bart, we'd like to present you with a little memento
of
your talk here today, and if you'll join me in thanking Bart for his great talk.
Thank you. Thanks.